Shutting down that. Okay.
Hello, everybody, and welcome to another recorded Zoom interview. And back for a third time is University of California, Davis geology professor Sarah Roeske. Sarah, the weather this afternoon, please, in the foothills of the Sierra Nevada of California.
It is a fine upper 50s, overcast, lull between two major storms.
Good. You got rid of that fog last time I talked to you?
Yes, the fog got blown out. And you folks, you're probably are you drying out from your big flooding events?
We are, yeah. There's major wind coming, but hey, this is not a weather report. This is geology now. Come on. And today, viewers, we're talking about the Brooks Range. To my surprise, when I first announced that I wanted to do an Alaska series, everybody wants to talk about the Brooks Range, and so I thought I would come right back to Sarah because she has experience. Sarah, do you have a guess as to why people are interested in the Brooks Range, just generally?
It is one of the best preserved collisional margins between a continent and an arc in the world.
Okay, well, there's an opening statement.
So there you go. It's rivaling the Alps.
Oh.
Let's just put it that way.
Holy cow. Okay, well, very good.
We just don't have nice Swiss cafes everywhere, you know?
Okay. Well, we've got Lexi the cat roaming in the background. We have Sarah ready to go. She's got a full deck of slides for us. Maybe one more thing verbally, Sarah, and then we'll go. Seems like you've been all over Alaska in your long career. What experiences or what projects were you on in the Brooks Range or in the neighborhood of the Brooks Range?
Oh, well, thank you for a great opening line. This is how I was introduced to Alaska in 1979 as an undergraduate, Middlebury College. I will put out a shout for liberal arts schools, and a group of us went to not the Brooks Range, but you'll hear the Ruby Terrain, which is part of the Brooks Range. So basically, I'm going to be talking today about everything north of the Tintina.
Good.
So the Brooks Range is a big part of that. But yes, everything north of the Tintina. We went into this area and we did a natural resources inventory for 2 months. A bunch of undergraduates with no supervision.
Yeah.
And we produced basically a resource inventory. It was 1980 when all the land in Alaska was being basically reassessed, and a lot of it was being put or given to and being, I'm going to say kind of not voted on, but tribes, corporations, as they're called in Alaska, Native American corporations were acquiring land. Mm-hmm. And so it was back when NSF had money for undergraduates just to go out and do stuff like this. It was amazing. It was just incredible. And so that got me going in Alaska. It was in that Brookian origin, Arctic origin, and the rest is history. And then I worked with USGS in that area in the late 80s. Mm-hmm. And then I got funding from National Geographic. And then I got NSF money. And then more funding from USGS. And yeah, so...
Well, you're a perfect person to talk to then. One more before we go to the slides then. We have been so obsessed with the Tintina Fault so far in the winter series that we've been doing. How do I follow the Tintina to the Bering Sea?
Oh, dear.
Is it an obvious thing? Does it transition?
No, it is very complicated, and that's near the end of my talk.
Okay, okay.
And that could have been that's another,
Okay.
But I will, that's a very good question, and that's something myself and a few others have thought about a lot. And a big part of it is it's really hard to get to.
Okay.
Study that area. So let's dive in and
Good. Please share your screen. Let's go for it. Yes, thank you.
So I think this sums it up is that these are some of the key people I've worked with over many, many decades. So Bill McClellan and I had a proposal funded in the 90s to work in the Ruby Terrain, which you'll hear about. Dwight Bradley and Allison. Allison's done most of the work in the Southern Brooks Range in the USGS in terms of she's compiled a big map. There are many people working in the Brooks Range. Many of them, though, focus on the Northern Brooks Range, where it's a sedimentary sequence, and it's a lot like the Canadian Rockies. It's a classic fold and thrust belt, so you're just stacking, and they're sedimentary rocks, and they're oil producing.
Okay.
So you can imagine that is where much research has been focused.
Sure.
And a lot of USGS work. So the schist belt, metamorphic rocks that I'll be talking about mostly on the south side of the Brooks Range.
Mm-hmm.
Allison was the one who did a lot of work in that along with other people in the USGS. And then Dwight was sort of all over the place in Arctic Alaska, but it's in particular kind of getting back to the connection between the Arctic Alaska and the terrains to the south, the Tintina problem, if you will.
Good, thank you.
So, and I should really acknowledge, I can't believe I don't have his name on it. Bill Patton was my mentor in the USGS. I worked with Art Grants also, and these are both old school USGS from the 1950s, 60s, and all the way through into the 90s. And Bill Patton in particular had done most of the mapping in the area where I was working, and he was beyond generous.
Oh,
so
very nice.
So these are all people that but of course, the big money, this is sort of the sad thing right now, we're looking at funding being cut for USGS and National Science Foundation. I don't know how we're going to get into these places again, because these are far remote corners of Alaska. Yeah, it's way out there. Yeah, so where are we? This is an old slide that is still kind of useful because it shows that I do think of Alaska in these kind of three parts, maybe more. It's now more complex than that I've worked in more of Western Alaska, but still, we were talking before about the Southern Alaska and the Border Ranges Fault and, kind of a nice story.
Yes.
That I think we understand pretty well from the Triassic to the present of an arc and a subduction complex. So the arc being the, Wrangellia Peninsular, Talkeetna arc and younger arcs, and then all the accretionary complex. And I did my PhD down here on Blueschists, so I'm a big fan of Blueschists. And then there are tons of Blueschists all through the Arctic. I'm just going to refer to it as the Arctic, and all this part of Alaska. And so it's a big chunk of Alaska that seems to have a separate history in most of the Mesozoic compared to the rest of the state. And so that's sort of the thing that's fascinated me is where and why, did they get, how did they get juxtaposed finally, but where were they in even the Jurassic compared, we don't really fully understand where these terrains were relative to North America, if you will.
Okay.
So the main point of Northern Alaska is it is essentially an arc-continent collision, and it's partially preserved. So that's the beauty of it. It's a lot of arc-continent collisions. You no longer have evidence of the arc that collided. So the Hatcher pattern here, so the continent part are in warm shades here of orange and this kind of deeper orange and brighter orange. These are continental rocks that were being basically stacked during collision.
Okay.
And they were being overthrust by purple is mafic, ultramafic rock complexes and oceanic complexes, accretionary complexes, and the reds are arcs.
Okay.
So we have an arc out here.
Yeah.
We have an accretionary complex, and we have a continent, and we have Blueschists. And I think we had this conversation last time. Your audience knows the significance of Blueschists, why they're near and dear to many of our hearts.
Yes.
Yeah. So they are recording subduction of a continental margin. So this Blueschist here is very different from the little bits of Blueschist we have down here. These are in oceanic rocks. So these are subduction complexes that record ocean subduction, not collision. Very different process here in the Arctic. The Seward Peninsula, the Southern Brooks Range, and what's parts of the Ruby terrain here all have Blueschists and very locally eclogite.
And from the pattern, from the stippled pattern, it seems like the belt of Blueschists to the north are far wider and more dominant than the little scraps of Blueschist to the south. Is that accurate?
That's mostly accurate. And I think it's partly, as you'll see in a more detailed map, there's a lot of Cretaceous plutonism that overprints the Blueschists. The Blueschists are all latest Jurassic, Cretaceous, early Cretaceous. There's some Cretaceous plutons right down here that really overprint it. So this may have all got to Blueschist facies all through here. But the bottom line is you'll see this is a sliver that I'm going to reconstruct and put back over here. So it's essentially a little sliver of the continuous subduction zone. That's where we're going today.
Thank you. One more before we move on, and this is probably stealing your thunder, but the continent of the arc and continent collision to the north of the Blueschists and the Brook Range, that's not our continent, right? That's a northern European piece of continental crust?
Yeah, and I'm not going to go into the Paleozoic history, but yes, it's not Laurentia.
Okay.
Yeah.
Yep.
In fact, I think that's the next slide.
Okay, great.
Yeah.
Thank you.
But your audience should know that this is not a setup. You don't know what I'm bringing next because you're always asking good anticipatory questions, right?
Thank you.
Yeah. So I think I just say, the point being that this has northern Alaska has a collision, southern Alaska does not, and so the accretionary history is very well preserved down there.
Mm-hmm.
Okay, so now let's talk the what's going on. North America is this sort of pale blue, and that's what we also call Laurentia. That was our mega continent before things got messy in the Paleozoic, if you will.
Mm-hmm.
And part of that messiness is all these terrains in here at Arctic Alaska and Farewell that we've mentioned a little bit, I think.
Yes.
These have, as they call, Baltica signatures or Siberian signatures. And so one of the talks that we had in our oblique convergence series, Maurice Capron and Joanne Nelson came up with a hypothesis quite a while ago now that they all emerged out of an Arctic Ocean a long time ago up here. If I kind of reimagine where things were in the Paleozoic, they escaped from Baltica and then were translated across through what is now the Arctic, and eventually collided with or were probably juxtaposed mostly by strike slip.
Okay.
In a series of events in the later Paleozoic, and that's been published on extensively by a number of researchers. So that recognition sort of tells us right away this area all through Farewell and Arctic Alaska experienced a very different history, at least up through probably into the Devonian. And then there's a lot of uncertainty where things were in, especially the Farewell, from sort of Devonian through Triassic. But the bottom line being, yes, this is very different history in the Paleozoic and Mesozoic, I would argue, at least until through the Jurassic.
Okay, you ready for a weird question?
Sure.
As I'm looking at this map, and I've seen it with you now, probably all three appearances, I'm guessing. I remember that you say the light blue with NA on it and the darker blue, AA. Your pet idea is that there's a major fault separating those two, and it's kind of a left lateral or sinistral thing. Yeah. Why wouldn't there be? So that's just you, or why wouldn't there be a major fault on everybody's map separating the light blue from the dark blue?
Well, let's go back one. Can I go back? I think I can go back.
If there's such different histories, you would think that would be the most obvious line to draw on every map going back 50 plus years.
Yes, you would think so. Okay. This fault is only recognized by very few of us. I was introduced to this fault by Bill Patton, who had done a lot of this. This area has very poor exposure.
Okay.
It's mostly quaternary.
All right.
And very few people have worked out here. It's hard to get to. Okay. But back in the 50s, 60s, 70s, into the 80s, Bill Patton and others in the USGS and based working in Alaska mapped all of this area. And he was fortunate enough to cover all of this area as one person. So he was trying to put it into one context.
Holy Lord.
And he and others noticed that the history of this area could not be correlated at all, if I skip ahead, with what we call now the Farewell terrain.
Okay.
And he has it buried in gray literature that kind of lingered there. And again, there's very poor outcrop in this area. So it was very easy for people to say, oh, we're just, these rocks are deformed too. And so they went, nobody really thought about it, I think, is probably one way to describe that.
Okay.
But he had in his great literature, and anytime you worked with him, he pointed out vigorously, there's an amazing collisional story in here that you simply do not see in the farewell. It's just not there. And so you go from a Paleozoic history being well preserved in this part of the farewell, lower Paleozoic carbonates that are deformed, folded, but that's about it. And they have a very different history from the Arctic Alaska terrain rocks up here, which are metamorphosed at high grade and overthrust and buried to depths of probably 40 kilometers or more.
Okay.
So why others haven't recognized it? I think Bill McClellan and I talked about it a lot. There aren't many people who have worked on both sides, if you will. So you have people who work in the Arctic. I mean, these are huge areas, right? This Arctic origin, when you stretch it out, the Blueschist belt's about 800 kilometers long or so.
Well, maybe I didn't ask my question as correctly as I wanted. I'm looking at primarily the northeast part of the map where there's light blue there. If it's been known for a long time that AA has a totally different continental origin versus the very light colored blue, North America and old North America, to me that would be an even more obvious strike slip fault than the Tintina. And is it the same question?
I think this part has not been known and it's still being debated. So this is work that's being done by Justin Strauss and Bill McClellan and others have worked on this now for at least a decade or more, and they have continuing projects in this area. This sharp line, I think, is partly my drawing. This is actually all overprinted by Cretaceous fold and thrust belt.
Okay.
So again, this is a very complex area. It's logistically very difficult to get into.
Yeah.
We're on the Canada-Alaska border, so you can't fly back and forth easily. But I think the main reason is they really, until we got a lot of detrital zircon data from in here, people have debated at great length what is the nature, what is the origin and even age of some of these continental rocks.
Okay. Well, thank you.
I greatly simplified in drawing this, extremely simplified in drawing this map.
Well, thank you. It's a detour, and it seems like I'm pushing for something, but I'm just coming at it from truly a newborn, looking at a map like this.
Do you want to start we can jump back and go to the reconstruction, which is what I have at the end, but we could go.
No. Let's keep going with what you did. I was just fascinated. I'm looking for major stories, and so far the Tintina has been such a major story for us, and I'm thinking that difference between European bedrock and North American bedrock would be a major story as well. But I'm hearing now that it's masked, it's concealed, it hasn't been thought about that much. It's not that big a deal, I guess.
It is a big deal, and I think the work that Justin Strauss and company have been doing in this area, they have a couple publications that have come out recently, will get more people focused on this problem.
Okay, all right.
But where these faults go is where and how they connect down here. I mean, if I go back again, you can see I basically am breaking. This is basically how I'm saying this is the major break, at least in terms of where I think you have to put some very major high angle faults, probably strike slip faults, and I would draw it a little differently down here. Now I would pull it up to here. But how this relates to the Tintina is the interesting problem.
I see.
Getting back to where does the Tintina go?
Sure.
I think it certainly goes down to some extent into this area. There's a whole series of faults in here that I don't have on this figure, but that are on this figure. So you can see there's 1, 2, 3, 4, potentially 5 strands of faults.
Okay, well, I can't stop. I'm sorry. I'm going to do one more, and I promise we're going to continue.
Sorry.
We've been thinking about turning on the Tintina 70 million years ago and trying to visualize what Alaska looked like 70 million years ago before you start shifting a bunch of stuff to the north on the Tintina. And to this point in the series, we've been thinking it's just open ocean, basically, south of the
No,
Tintina. No.
no,
So
no.
just looking at this map at the
Oh,
most,
south of the south of the Tintina.
yeah,
Hmm.
nothing's,
Yeah.
if we're,
Well, the problem is always the farewell.
okay,
That's a big. This is a continent block, and it has basement as old as 2 billion. So
okay,
this is not a trivial piece of real estate
right,
in terms of reconstructions and how to think about it. But yes, this is so getting back to here's our arc. Here
yeah,
are arcs.
yeah,
Here's Mesozoic basins, late Mesozoic basins. So
right,
yes, this is relatively open out here,
mm-hmm,
but it's still um yeah, it's hard to describe. I think the question this all of this terrain has already been displaced by the time the Tintina kicks in at 70. I think there's an older phase of the Tintina, but
okay,
that's what we'll talk about near the end of this
sure,
talk. But
okay, all right,
I think the if you reconstruct the late stage of the Tintina, then most of that you could put onto known faults.
huh,
That there's that amount of slip does, the 450 or whatever approximately kilometers that Canadians have documented, you can easily take up on a series of strands through here.
okay,
But that doesn't explain how you get farewell next to Arctic Alaska.
right, right.
I think there's an older story in here.
Okay, that's enough of a detour. Thank you for being a good sport.
Okay.
Let's motor on to
Okay,
the
but
Brooks.
those are, well, you hit on those are the big questions. Is
Okay.
where does the Tintina go,
Yeah,
and
yeah.
how does Arctic Alaska get juxtaposed with North America?
Yes,
Yeah,
yes. Okay, thank
those
you.
are the questions. Okay,
Okay.
so the reason I like to talk about the Brooks Range is because I'm a big fan of Blueschist and eclogite.
Mm-hmm.
I brought a pet rock.
Mm.
This is not from Alaska. This is Franciscan.
You want to stop your share for a sec so we can see this thing?
Oh, sorry. Yeah,
Yeah.
that would help, huh? Let's see. Stop share.
You got a piece of the Brooks Range right there.
No, this is Franciscan.
Oh, okay. All right.
But
Okay.
they have rocks like this in the Brooks Range.
Okay.
Same rock, very similar rock. But I'm not going to haul a big piece of this out for just a pet rock and a helicopter. So your audience probably can't see, maybe there's glistening things in here. There's garnet,
Okay.
and it's kind of a steely blue color and a little bit of green. And so
Okay.
this is glaucophane, garnet, clinopyroxene with a high sodic component, which we call amphasite. That's an eclogite.
An eclogite. How's that different than a blue schist?
And eclogite is even more cool than blue schist, some would say. It's basically the higher temperature and locally higher pressure equivalent of a blue schist.
So if you go down a subduction zone, you go green schist, you push it deeper into the subduction zone, it's a blue schist. You keep going, it converts into an eclogite?
Broadly, yes.
That's my wheelhouse.
Sure. Why not?
Yeah.
Broadly.
Why not? Okay.
I do have a slide actually on a couple, but I won't spare you jumping ahead. We'll get to that.
Yeah.
I actually put a metamorphic facies slide in today because it is relevant.
Okay.
I think it's coming soon. But
Good.
you can think basically both blue schist and eclogite, I should say what we call low temperature eclogites, both require a subduction zone system. They mean that you're taking rocks down fast enough that they can't equilibrate to our global geotherm. And so they're cold.
Okay.
At any given depth, their temperature is very cold. And that produces a unique assemblage of minerals like glaucophane and amphasite.
Thank you.
So there we go. So you can see there's a lot of it, as I had on the earlier slide. We know, we have a pretty good idea. Let's rephrase that. One of the challenges in the series is getting good, accurate ages on the peak metamorphic event. We have cooling ages that are around 120, but the peak metamorphic event for burial, we want to know what was the time when we really were stuffing continent under an arc or into a subduction zone, is probably in that, based on a couple different abstracts mostly, and one age I have from down here, we think is between about 145 and 140 million years.
Okay.
So That's the Jurassic Cretaceous boundary.
Mm-hmm.
There's whiffs, very tantalizing whiffs. There was something going on here between 170 and 160. And I think there we go. This is again, a very sensitive mouse, so I need to stop moving around quickly. The direction of subduction is the same for both Arctic Alaska, and this is the Ruby Terrain, this little sliver of blue.
Okay.
So Seward, Arctic Alaska, Ruby Terrain, or Brooks Range. So that's kind of the first part of the story that's key. So we have to reconstruct this in such a way that it makes sense that all these pieces were basically parallel. And then the other part of the story that really doesn't get talked about, but I think is useful for thinking of reconstructions, are these little purple dots all over the place.
Okay.
These are mafic ultramafic complexes, and they're quite large, and they're spread out through the sort of more interior part of the Brooks Range. And then there's, even though we're putting them at scale, but there are numerous little dots of these all down through the Ruby Terrain, and then there's quite a large blob down here. So I have another figure later, but these, Alice and I in particular, and others who've worked in this area, interpret this also as arc basement. And not all of them are strictly arc, but they're four-arc or arc. So we have two phases of arcs. We have an older phase that we'll get to here shortly, and then this younger phase. And the younger arc is the one that's really well preserved. That's what we call the Koyukuk arc.
Mm-hmm.
So that's kind of the what do I say, the collisional part of the story. But then how do we get there?
And before we leave this,
it comes up right away. Sorry.
Yeah. Before we leave this map, what portion is the Brooks Range proper, and what portion of this story so far is south of the Brooks Range?
This is Brooks Range proper.
Okay.
Right here.
Yeah.
Seward Peninsula is, I mean, if you reconstruct, it's pretty easy to slide the Seward back to the Brooks Range. And I would argue it's also quite easy to basically take all the strike slip faults out of the Ruby Terrain, this little sliver, and it stacks up to a much smaller piece these are Cenozoic strike slip faults in part. So we can reconstruct, shorten the Ruby, and then slide it over on Koyukuk fault here, and then sort of tuck it into this part of the Brooks Range. So that's why I would say, for all intents and purposes, all of these terrains went through the same history together until at least 140 million.
Oh, they're kind of dismembered? Each of those little candy canes were all used to be together?
Broadly.
Yeah, cool.
And that's where we're going.
Nice.
Yeah.
Okay.
Yeah. So and that's been known for a while, but there's been a lot of debate how they were separated. And I would say a prevailing view that I don't think we have evidence of is that this is an extensional complex, and these were just extended apart in the early Cretaceous.
Okay.
And that doesn't work because this is a early Cretaceous arc.
Well,
so,
yeah.
Okay, Blueschists, let me just quick show. Yeah, so here's your assemblage. You have relatively cold temperatures and high pressures.
Mm-hmm.
Your normal metamorphic field might be out here.
Mm-hmm.
Normal geothermal gradient. The Ruby Terrain, the schist belt is what we call the Blueschists in the Brooks Range, and then the Seward Nome complex all have very similar, what we call pressure temperature paths, and they all intersect kind of a similar range of peak metamorphism. And where we have ages, it looks like in the Ruby Terrain and in the Southern Brooks Range, these ages are around broadly 145 to 135-ish, 140.
Okay.
So slam dunk, they all went through the same history is kind of the bottom line.
Okay.
Yeah. Okay. So there's this older component, which again hasn't received much press, understandably, because it's not preserved. But this gets back to all of this area, again, which is a really big area, went through the same history together. These ages are from these mafic and ultramafic rocks. And locally, some are igneous zircon ages, and a lot of them are actually amphiboles from, there's a décollement surface where these mafic ultramafic rocks are thrust over much lower, basically pillow basalts and seafloor basalts. So it's been documented that some of these are recording fairly high pressures. So these are rocks that are at the base of an arc. Some of them are as high pressure as 10 kilobars, which is, 40 kilometers or so, 38, 35, 38, 40 kilometers, depending on exact pressures in some of these complexes. So these were basically displaced over their accretionary complex at this time. So there's an older phase here of abduction, if you will, is the term that people like to use.
Okay, I'm going to step in. We can keep with this slide, Sarah, but I'm starting to lose it slightly, and let me try.
That's okay.
Let me try to rephrase from not only myself but the audience, or many in the audience, perhaps.
Yeah.
So, Brooks Range, I see a bunch of purple on the map. So I go, okay, there's a bunch of blue schist related rocks in the Brooks Range or in the neighborhood of the Brooks Range, and I'm thinking, oh, so the Brooks Range is the result of subduction of an oceanic plate, but you're not saying that. You're saying that there's an older history of a volcanic arc that then eventually collided with continental crust to make the Brooks Range. Is that where we are so far?
Yes.
Okay.
So blue schist in northern Alaska did not form the blue schist. Let me back up. It is complicated because the blue schist that is in the Seward, the Brooks Range, the Ruby Terrain is formed in continental crust. It's not an accretionary complex.
In continental crust.
Okay, so you're taking continent down into a subduction zone. But there's an older history where you do have some blue schist in these purple rocks. So this might help. Let me jump ahead.
Thank you.
I think this will go, yes. Okay, so the stacking might help. Okay, so what we're talking about is, again, purple is always ultramafic, the way geologists like to run, and blue is going to be our blue schist.
Okay.
So we have basically accretionary complex, Zentner, and then locally above that, not shown on this schematic block diagram, are these mafic ultramafic rocks. So we sort of skipped ahead here, but we have here's our purple rocks. Then we have a little bit of slate. Then we have the schist belt is basically composed of very quartz-rich, mica-rich, mostly where we have ages, Paleozoic, detrital zircon ages, Devonian and such. These have Devonian ages. And then below that are what a whole series of complicated terms. Central belt is also locally metamorphosed blue schist. And then Endicott Mountains, Lochthon are Paleozoic carbonate and siliciclastic platform rocks. A lot of it is carbonate. So you have a continental margin, basically. A Paleozoic continental margin that is being successively stuffed under an oceanic complex. So you start with ocean out here on the arc, and you're bringing slivers of distal margins. So distal margin being your slate, then more proximal. I think these rocks might have been also fairly distal locally. So there's some of it is almost cherty, but it's very silicious, not a lot of mica. And then these start to look like you're on the margin of a continent, which you were, and then you have this. So this whole stack, basically, as you go north through the Brooks Range, is preserved quite beautifully. And so that's why this is studied extensively as a classic imbricate slicing, as you basically bring in a continent and you just keep shortening it. And there are estimates of total shortening across this area, all through here, of over 400 kilometers. So this is a very impressive pull and thrust belt.
It is. And can you remind me of when we were doing this pizza box stacking of those little sheets?
So the pizza box stacking was basically in the Cretaceous.
Okay.
And continued into the late Cretaceous. The earlier phase, the collisional phase,
Yeah.
is late Jurassic, early Cretaceous.
Okay.
And there's an even older phase that I was probably, I could have maybe left it out, but I like to talk about it because it's important, because it's how we get these ultramafic rocks that have an older history at the top of the stack.
Which have nothing to do with the other purple things of the ruby.
Now, these purple things here
Yeah.
are the same as these
They
purple
are.
things.
Okay. Okay.
So you can see it was a major
Yeah.
complex of mafic, ultramafic rock.
Yes, totally.
Yeah.
And this is part of this Alaska Z, right? This big capital Z on a map.
Right. Which
Okay.
I don't call it a Z because it's not. It's
a 7?
It's not. The Z means that the ruby terrain would have had to have been flipped over. Isn't one way to put it.
Okay.
I'll just say that.
Yeah.
And so I don't call it the Z. A lot of people have called it. Have used an oricline to explain this, but then the Blueschists should have been not. Our direction of our polarity of subduction would have to flip, or the direction of subduction. If this is wrapped around, you can visualize, well, then it should be going the other way, and it's not.
Okay, well, I'm impressed. Number one, you're doing a great job. Number two, I like the big scale of this. I didn't realize, I know it's complicated, but at the same time, this is kind of pleasing. Like, I didn't realize there'd be kind of major patterns here that we're seeing at this scale. That's exciting. And
it is, yeah. So I think when we start to put this all together, like I said, this was on the scale of, well, certainly bigger than the Alps.
Yeah.
I mean, it really is one of the best preserved examples of an arc-continent collision.
Okay. Well, one more then. So before you move on, so the headline is, this is what you just said again right now, and you also said at the very top of this interview, this is one of the best preserved arc-continent collisions. So are we looking at the arc as well as the continent? Are we seeing the Koyukuk? That's the arc that you're talking about.
Yeah, they're two arcs, but we'll focus probably the rest of this time on the Koyukuk.
Okay.
Because there's this older arc that's been thrust over the margin.
Right.
Then there's a little pause, if you will, and then the Koyukuk, about the time this is getting thrust on top of something. Well, let's move ahead.
Let's go.
Okay, let me get back to where I was. Just get my brain going here. Okay, so what I'm talking about here, it is confusing. These Blueschists that are really the focus of the talk, and how they formed. These are these 145 to 140. So we'll just keep that in our memory banks.
Good.
So, and that is during collision of Arctic Alaska continent with the Koyukuk arc.
Thank you.
We'll go run with that.
Yep.
Then there's this older history that's preserved as these little Klippe, if you will.
Got it.
Klippe is a fun word, I think, German, where they're basically little slices left, or most of the peat box got eroded away, if you will. And, but they're, again, the point being, they're the same Klippe all through here. So whatever reconstruction we do, this was all one continuous sequence.
I love that.
And it's not that this got folded around. I will argue this got slid back.
Okay.
Okay, so that's where we're going.
Yep.
Then here's our stacking order.
Right.
And so getting back to what you were saying is, well, why are there so few, it's kind of a scrawny little Blueschists down here.
Yeah.
This orange blobs all through here are plutons that are between 120, and most of them are between about 114 and 110 million. And they pretty well invade the schist. And so they overprint the Blueschist in most places, is my guess. But they are so pervasive that we really don't know. Okay, so as you can see, there's a lot of, this is all this in green. This is a slide from Alison Till. She gave a great talk at, and I think this was in Vancouver, GSA, quite a while ago. All this green is tertiary deformation. So that's a really important component of trying to unravel the history of this area. As you can see, we have a lot of shortening, fold and thrust through here. We have a big fault called the Koyukuk Monument Fault System. We have Caltag fault, which is a sliver probably of the Tintina, a couple other faults. So there's a lot going on in the tertiary that we have to deal with.
Why? I figured that would all be dead up there. I figured the Brooks Range would be dead and everything's like just like the Appalachians. It's just seen better days. Not?
Oh my. Well, they had a 6.7 or something earthquake a couple of years ago right up in here.
Up in there. Huh.
Oh yeah, this is seismically very active. I
Huh.
could show you some slides that are,
Okay.
but all of this part of Alaska is just lit up seismically. Not huge earthquakes, but 6.7, that gets your attention.
It does, but you wouldn't say the Brooks Range is active tectonically.
Yes, you would.
You would?
Yeah. Oh, there's quaternary deformation in this part of the Brooks Range. Actually, I'd have to move this figure, but yeah. Yeah. Okay. That's another hole.
All right.
Yeah, the Northeast Brooks Range is active. This fault system is locally active.
Okay.
Yeah, it's not dead. Yeah, there's active rifting out here in the Bering Sea. Yeah, it's pretty. Actually, there's almost no part of Alaska that doesn't qualify as active tectonics. So it's not like Appalachia. It's not. Yeah. It didn't go old and cold. It's what we tend to call, what's the term, a mobile belt. It's really hard to define where North America is when you use GPS in Alaska.
Yeah, it makes sense more than I think about it. Yeah. It does make sense. Okay.
Yeah. Anyway.
Yeah.
Okay. So just this is Jeff Amata, who was a PhD student at Stanford working with Elizabeth Miller, and he did and continued to work. He was mostly in Chukotka in Siberia and in the Seward Peninsula. But as I was putting this together for the Penrose conference, I came across this paper that I'd seen before and it hadn't really clicked. And then it clicked. It was like, oh, he describes this arc at 200 million, and he didn't call it the Canute arc, but I'll say, yeah, I'm going to call it the Canute arc. He has this is straight from his figure, that there's this distal arc, possibly locally built on continent, maybe not, certainly not all of it, that is sweeping in. And here's northern Alaska. So this again would be Seward Brooks Range, and I would argue Ruby.
Oh, wow.
So that's just to kind of put it in a context of this is the beginning of we have all these ocean complexes all over, tossed on top of continent. And I think this is where that all originated. So I think the other reason I like this is he separates the Anguillutum Ocean and Slide Mountain with a big transform. And if you've been talking about Canada, you've probably been talking about Slide Mountain.
A little bit, but not much. So I can't.
Here's our buddy Rangelia.
Right. So is anything on this map in place Alaska that we would know? Is it down there in the south by the Slide Mountain thing? Is that part of like northern Alaska?
So this would be, he hasn't reconstructed Yukon-Tanana.
Okay.
This is Yukon-Tanana.
I see. Okay.
And this is Farewell.
Holy cow.
He hasn't taken, we know there's a lot of displacement here. So those are,
Man, okay.
He was so I think the main point of his view of this was saying these two oceans that a lot of people want to say are the same ocean were separated by a transform. And as far as I know, he's the only person who said that. And I thought I would agree with that. And I think that's part of an interesting, so for people doing really large scale plate tomography through this area, I don't know if the recent models have incorporated ideas like this, but I think those are important ideas. So, okay. But let's move on because all we have left of this history is some of this mostly eroded away in clastic sediment. We have a record.
Wow. Okay.
Yeah. So, okay, moving on. Okay, so then the broad view is we have this very long-lived Anguillutum, which closes beneath this. We're going to call it the Michigook-Canute arc. It's Michigook in the Brooks Range, Canute in the Ruby Terrain. And then, so here's our arc that's now just little scraps. And here's the accretionary complex, which becomes the Anguillutum terrain, or accretionary complex. And then somewhere way out here, we have Arctic Alaska. We don't know where it was exactly.
So we, at this time, do not have subduction under North America. We have it
Correct.
Subducting away.
Correct.
Does everybody see it that way?
Yep.
Wow. Okay.
I think everybody, I don't think many people This is pretty recent that people recognized. And again, it was mostly Stanford students
Okay.
getting a lot of work out of the Southern Brooks Range. A couple of students. And um, I think so this is probably in the last, I would say, 15 years that there was recognized. This is a pretty long-lived arc and it almost certainly had to be subduction away from a continental margin.
Okay.
Yeah, and actually, this is where, some people want to have a lot of subduction away from North America. I think the one place we know for sure it most likely was a long-lived away from North America is in the Arctic. And there's really no other way to explain how you have a passive margin preserved for a long time that then goes into a subduction complex and collides with an arc.
Very interesting.
So so then something happens very interesting around 160, 165, and that's where a lot of people say that's when subduction initiates. I would argue we're just pushing there's something happens. Maybe we have initial underplating of some thinned margin. There's some kind of large scale event around this time period where our arc gets thrust over its accretionary complex. That's our Michigan Canudi, and that's the little scraps that are at the very, very top of our stack of pizza box. It's a very regionally extensive arc thrust over accretionary complex. And about that time is when the Koyukuk arc starts up. So this is work done by, again, Bill Patton and Steve Box, who was working with the USGS at the time in the late 80s.
Now, where is that arc at that time? Is it south of Alaska and we're about to collide it to make the Brooks? Or are we in that inland passage thing like we were looking at with that Stanford student?
We don't know.
Okay, that's fine. Yeah.
I will tell you the probably some of the biggest controversy that still goes on in the Arctic is how the Arctic Ocean opened. And I'm not even really, I'm going to touch on that very lightly because that's another whole topic and I haven't studied it that much. And that's something that could be a whole separate talk that I shouldn't give.
Well, Sarah, this is really good for me, and I think the audience. We know some of these concepts. We're trying to piece these stories together. We know we're not going to solve everything. Nobody's solved everything, but to be able to just try to keep track of these moving parts. I mean, I'm optimistic right now. I shouldn't be looking at something like this, but I actually am. Like I think we can really kind of make some sense of on a major scale like this. And so this is perfect for where I am personally. So thank you. And you're saying, hey, I don't want to go here and I don't want to go here. I haven't thought about it, or that's a different talk and I'm not the person. That's totally fine. But that this is just right up my alley. So thank you. Let's keep going.
Okay. So we this is the remnants. This is the remnants, as I said, of our Michigan Canudi arc.
Yeah.
These purple blobs. And some of these purple blobs, and then they're, especially the deep purple, and then they are on top of the Zangiyuchim to Zentner. This stacking is what happens once you start to bring this continental margin of, here we are, what we're going to call power tectonics. We're bringing our continental margin underneath the Koyukuk arc. Now, where this was in real space, good question. We can arm wave about that a little later. Okay, so getting back to this slide, here we are. So we have these two arcs. We're focusing on subduction to the south. And so now this phase of subduction, as best we can tell from chemistry in the arc and age of those rocks, their chemistry changes. It starts again around 160, 155. And most of the arc is starting to taper off by about 135, 130 in terms of volume, but also the chemistry changes. And this is a really nice paper that Bill Patton and Steve Box, series of papers, and others. There was a lot of interest in this Koyukuk Basin, basically in the 80s. oil companies were flying all over there. And so there's quite a bit of data companies were flying all over there. And so there's quite a bit of data from a fairly obscure part of Western Alaska. And so that we understand that this arc was waning and starting to get basically components that look like subducted continental material around broadly 135 to 130.
Okay.
That's why I selected this time as subduction from a subduction model to basically collision. So our arc basically starts to die
Yeah.
because there's no more mantle wedge. You're just stuffing continent under it. And our stacking continues because there's still slab attached.
So we're
And so this is
so we're,
yes, we're still pulling the continent under,
yeah.
but it's now because we're subducting continental material, we lose it's buoyant. And so the classic problem, if you're going to have arc volcanism, you have to have an asthenosphere wedge here.
Right.
And once you start to bring buoyant material in, you're starting to close that. And so your arc dies.
So we're killing the arc. We're killing the blue schist factory, and we're starting the pizza boxes, or we're just continuing the pizza boxes.
We think based on clastic sediments, quartz clastics piling into this area. I believe it was around this time. I want to say it was near the Jurassic Cretaceous boundary, so 145-ish. So we're already starting to produce topography on our continental margin that is bringing quartz material in, and you start to get blue schist clasts and blue schist minerals into those basins. So there's been a lot of work looking at basins in this area that are still very well preserved, and there's been much more work one could do.
And this is the beginning of the Brooks Range topographically?
Yes.
All within the AA.
Well, it probably was in other terrains to the Seward and the Ruby, but they, in the process of being translated away from the Brooks Range, lost most of their cover.
Okay.
So we don't have the nice stacking sequence preserved in most places, except in the Brooks Range, the northern Brooks Range.
Okay, I'm starting to see it. Thank you.
Yeah, so it basically, this is the simple view, but I think it's reasonably accurate that you're basically taking a thick continental margin, bringing it under an arc, and you just keep piling it up. And some of the most significant shortening actually propagates west into Siberia. So by mid-Cretaceous, early to mid-Cretaceous, say 120 to 100. This part of the margin goes into a locally an extensional phase, which we would suggest is due either gravitational collapse or simply you're changing the dynamics of the margin. So this is no longer shortening right here, but you're continuing to shorten more inland. So you have extension on this side, shortening on this side. I'm jumping ahead, but this is like 120 to 100.
This is perfect. This is perfect. Are there magmas? I'm sorry, go ahead.
And so then you have tons of shortening up in the Siberia, so up in this area, and then sediment just dumping into basins in here. And so this is what's forming, again, what the oil industry gets very excited about, because you have all this clastic material come in on top of a bunch of carbonate.
Off to the right, is that sediment being shut off to the right in that cartoon?
In this cartoon, the sediment's coming from Siberia. I really should go back to a map.
From Siberia. Oh, I see.
Yeah, so the sediment,
okay.
It looks like the maximum exhumation uplift areas were up in here. When we get into more the kind of closer to 120, 110, 100 phase, and you just like huge volumes of sediment are coming from the west to the east, and you just piling sediment into these basins. So it wasn't topographically high, it was a low.
Okay.
So you have a switch, basically. If we go forward, at this phase, everything is in a shortening mode. And then as it continues to evolve, like most arc continent collisions, it's sort of hard to put your finger on, when a lot of people ask, when did it collide? And you go, well, how do you define collision, right?
Right.
Is it when you pour? I argue collision is when you have blue schists in continental rocks.
Sure.
That tells you've taken the continental margin into the subduction zone.
Well, we probably fail the slab as well, right? We pinch that slab off down below.
It can keep going for a long time. Yeah, the Himalayas have been colliding for over 40 million years. India has been subducting under Tibet and Asia for over 40 million years.
Okay.
So if you have enough slab, if you have what they call slab pull going on for a very long time, this can be going down 600 kilometers. That it takes, at some point something gives, and I think myself and a lot of people would say what gives is new forces arise and you open the Arctic Ocean and you start getting strike slip and you basically start to terminate things because the downgoing plate gets dismembered. But yes, that's always an interesting problem of how long could you be continuing to subduct continent. There's pretty good evidence you can subduct it for tens of millions of years after initial collision.
Well, I love this cartoon because it's similar to what we've been looking at down in the lower 48 and British Columbia as well, where we're trying to visualize an arc colliding with a continent. And here's everything in this collisional suite, as I call it. And it's playing out right up here in the Brooks Range. I mean, I'm very excited about this.
Yeah, and as I said, it is well preserved. We have all these elements still preserved.
Wow.
Yeah.
Okay.
So then this part, this strike slip fault, is my hypothesis fault. I will take blame, credit, and I juxtapose it against this cut here. But this cut, it turns out later, I think, is getting back to, that's our boundary, I would argue, between the Arctic and North America. So this comes into play later.
I see.
But yes, so the idea being that we have to have a way after, if we go here, this I was talking earlier about, we had a shared history of the Seward and Brooks Range and Ruby until at least 140, and probably I would say even 130 million, because they all record Blueschist metamorphic events about that time and about the same pressure and depth. And so to say they weren't somehow all continuous or contiguous, at least, it would be just too much coincidence. So I think, okay, so it's a shared history, and then things start to unravel. And in this old picture, I have that basically what I call the Ruby Fault comes somehow magically out of North America. And this time I had Arctic Alaska or Arctic Ocean Canada Basin opening by a rift oriented like this. But in any event, my hypothetical fault that's dextral slip basically is Ruby terrain is this piece of Blueschist that escapes from the collisional system and comes shooting out the side. And partly this was based on things that are happening right now in Southeast Asia, north of Australia. So we all invoke Southeast Asia whenever we want to talk about active tectonics, because you could find anything you want, right?
Yeah,
Especially when it comes to continent arc collision.
Sure.
So we all look down there, and there's some very large scale strike slip faults. Just if this is Australia and it's moving northward, and there's a whole series of arcs between it that are having their subduction zones jammed by this monster continent of Australia moving on them. And what fascinated me was realizing there's faults in there that are basically like this. They truncate arcs and are just flying out, and continental slivers and collisional complexes are just flying out the side.
But that strikes. I'm sorry. Go ahead.
Okay. Yeah. So basically, it's an escape as things are shortening and possibly rotating. So that's how we double up, I would argue, with our Blueschists. We have Blueschists here, and these Blueschists used to be over here, but now they're getting translated out. And then about this time is also when we start to get all this Plutonism in here.
We're dismembering the Blueschists, but why are the Blueschists at the surface? When are we doing this crazy uplift?
Yeah, the uplift, the exhumation, I show them as at the surface. The fission track ages, which again are recording very shallow cooling events in the crust in this area, are around 70 million. So, but we do see, but I should add, there's clastic material all through this basin that is records major erosion and exhumation starting around 100
Okay.
110 million. Albion. So the Albion time period, and it's coarse clastics. So we're dumping material from this margin into this area.
If you wouldn't mind going back to the cartoon that I love so much, right there, we've got the Blueschists down below the surface in the block diagram, and I guess
Yeah, so
I would expect those Blueschists to be popping up in between 130 and 110 or something. I guess but that's not the dates you have. It's younger than that. You say 100 to even as young as 70 to get that stuff way.
well, so the 70 might be a regional cooling. I think.
Okay.
Wait, we don't actually have record. We have record in the Arctic,
Mm.
in the Brooks Range,
Mm-hmm.
of Blueschists in clastic rocks by, I forgetting I want to say by broadly 120,
Okay.
but I'm don't quote me on
No,
that.
that's fine. That's fine.
There's a clastic basin, and I don't know how well it's dated. It might be even a little older than 120. I think it is older than 120. So there's a clastic basin here that has Blueschist fragments in it, presumably derived from this schist belt, and that records certainly then exhumation. So you can have exhumation of the Blueschist happening as you're continuing to subduct, and you probably did.
Mm.
But if you don't have a basin to record it, you wouldn't know because you've
Mm-hmm.
eroded the rocks away,
Yeah.
right?
Yeah.
So in the Ruby terrain, we don't have a basin neatly preserved like we do in the Arctic Alaska. What we do have around the border, if I go back to the map,
Yeah.
there's a schematic map, what we do have around this border is clastic rocks that record exhumation of, it's what we call inverted metamorphic or inverted sequence. So the base of the basin has the ultramafic rock class, and then you get more mafic, and then you get basically bits of pluton mostly, and some of the schist. And that again is Albion, so 110 to 90.
Wow. Okay. Well, that sounds like Trevor and Sean down with their big collision at 70, the inverted thing, which I still can't picture. But anyway, that we can
Yeah,
deal with that later.
so you basically, as you have material being exhumed,
Mm-hmm.
your basin is going to record.
Oh, I see. Yeah.
Right.
It's upside down.
So
Yeah.
you imagine you're bringing this up and you strip material
Right.
off.
Right.
So yeah, they're talking about inverted metamorphic belts. I'm talking about just
I see. I see.
you just bring up
Yeah.
dump. Yeah. So
Yeah.
your top of the sequence will be your deepest rocks.
Okay.
Your top of your stratigraphic sequence will be the deepest rocks coming up.
I'm laughing because I'm loving this, and we're over an hour. Let's keep
I
going.
know. I was
Like
thinking.
this is.
Yeah, I was gonna say. Yeah, we're going a long ways here. I will be the first to say it's a huge area, and it is frustrating if you've been thinking about Southern Alaska and Canada, because I will be the first to say how this all relates to Southern Alaska and Canada. At this time, I would say they don't.
No, they don't. Right.
They don't.
Because
But it's a big part of Alaska. Yeah.
it
So if you're going
is.
to talk about Alaska, but it's when we started our first discussion back in late summer, I think.
Right. Right.
That are you going to cover Northern Alaska?
Yeah.
And you're like, I don't know if I'm going to go there. So now you can think about.
I'm here
do I
now.
really want to go
Yeah.
there?
No, this is
Yeah.
great.
I'll try to get to the point of why I think it becomes important in the Cretaceous.
Good.
But
Good.
these really are cool rocks.
Oh yeah.
Yeah. So this is where maybe we're starting to get a connection with the rest of North America.
Okay.
And so this again was one of those aha moments when you see a paper and you go, oh, I really like that. This was a different view of how the Arctic Ocean, Canada Basin in particular, opened. Prior to this paper, almost everything, people had what they called the windshield wiper model. So Arctic Alaska was like this against Canada, and then it rotated.
Mm.
And there is evidence for some rotation, but the amount of rotation and didn't quite make sense.
Mm-hmm.
And there were seafloor anomalies in here, but they really were hard to determine the age. So you and your audience may know there's a lot, what we call the long Cretaceous normal.
Yeah.
And so it's hard to get dates.
Sure.
And so anyway, unfortunately, because of all the polar ice cap melting, fortunately for science, unfortunately for everything else, the result is all of a sudden they could send ships in there and do a lot of detailed tracks to get better magnetic anomaly information. So it was really just the fact of the polar ice cap melting in this area. Before this, they could get icebreakers in occasionally, but that was about it. So once you could no longer needed icebreakers, people started doing more cruises, dragging magnetometers across this area, and this Arctic Alaska view came to be. And it's not this person, and others have also described these magnetic anomalies and argued that basically this margin was a very oblique extension, and it was fairly short-lived. So the Canada Basin isn't that large, and there's continent all around it. That basically where that's going is, I think this is our fundamental boundary, is a sinistral fault. It's not just a rotational boundary. So here's where, if I feel really bold, I'm going to draw my sinistral fault.
How can anybody argue against that if there's North American craton, basically? That's going too far, but anyway, there's North American.
No, this
rocks.
is craton. This is craton right here. Yeah.
I don't get why that's controversial to put your red line in, except you're just saying nobody's thought about it, I guess. But like, to me,
a few of us have, but nobody's quite been. I think there's definitely, as I said, Justin Strauss and Bill McClellan and others have argued that there's a big sinistral fault through here. Where it goes from there, nobody else was talking about, and I was like, well, why not?
Good.
So I just dashed it in as if there was no offset. This fault, I would argue, is forming at about, again, the time frame of this opening would be around probably 130 to 120. Not well dated, but broadly 130 to 120 is the opening of the Canada Basin. And then we know the Tintina fault came along. And so all these tertiary faults are offsetting my big sinistral fault. So this is just a sketch fault, if you will. It's not reconstructed. So then this basically is just highlighting, this is, again, this article, these are his age constraints. So as I said, because of the problem of dating anomalies in that time zone, it's not well constrained, but that's the evidence. Okay. So here we go. This is the kind of, we're winding down here. This is the reconstruction I think I've shown you before.
Yes.
Yeah. So I can go back and forth. Lexi says, why are you still talking?
Oh, Lexi, I'm sorry, Lexi. You need attention from your mother, but I can't stop with your mother. And I'm before.
Yeah. So I was just going to say that I go back and forth on whether a lot of this is dextral or sinistral.
Oh.
So if you want to say a lot of it is dextral, then there's a lot more displacement than the Tintina. There was probably, I would suggest, an older phase of the Tintina that was, or some fault that was dextral, that was displacing these slivers, and that they were offsetting. This is the sinistral fault in red, so you have just scraps of the sinistral fault left. And in some ways I go with that now, because rather than one long sinistral fault, because if we go back, you can see that he argues that it was a pretty minor, short extension. This is still large, and this is straight from his figure. This is farewell terrain.
Yeah.
North America, Yukon, Tanana.
Right.
So this is basically, if I, we're going to switch orientations on you, but this is where I came up with this figure, and then this figure. So now we're just flipping it around. Here's farewell terrain, North America, but then I've offset that sinistral fault with dextral faults.
So maybe this helps me and the viewers. So today's drama of a major kind of reddish arc colliding with a continent, kind of the mauve stuff to the AA, It's unclear where on this map that collision happened. It could have happened way off the map to the north in the Arctic or something.
It must have.
It must have.
Yeah. So this gets back to the idea of the transform boundary between Arctic Alaska and North America.
Right.
This was essentially happening on a separate plate.
Separate plate off the map. So then why? So then not even the Brooks Range. If we, I don't know, just to finish up, 100 million years ago, Sarah, how much of Alaska is in this field of view right here?
Oh, by 100. Yeah, by 100, probably all of this.
Okay, let's go earlier.
So if we go
before the opening of the
so
Arctic.
This was all probably, pretty close. If we get back to, I think we can with moderate confidence reconstruct at least the tertiary faults.
Okay.
And even the dextral Cretaceous faults, we can do the cookie cutter pretty well. So I would say all of this was, plus or minus hundreds of kilometers, but not thousands of kilometers.
But 180 million years ago, there's
180
there's nothing
and 140,
on this map.
Right.
Yeah. Except for the light blue North America. That was
and probably Farewell.
Okay.
Yeah, so Farewell again did not play. Farewell did not play in this game at all. And so this is the big boundary we talked about right at the beginning. This has got to be some major boundary that's very poorly exposed. And where exactly it goes when you lose Farewell, here we have our lovely question of Togiak. And we have basement of Farewell down here that's 2 billion years old. And then we have this Nyack arc that we don't understand.
Okay.
And exactly how this all pieces together is something I hope Trevor will figure out.
Sure.
There's Blueschists down here that aren't well dated. We don't know what they relate to.
Well, are we sure Farewell is different than Yukon-Tanana? Why wouldn't that just be?
Yes, it is Baltica. It's very different.
Baltica, but
it's Baltica.
But it doesn't play this game.
It doesn't play this game.
What the hell?
I know, the nerve, huh?
Okay. All right.
The Farewell is so beautifully preserved that, paleontologists love it. Let's put it that way.
They do?
To me, it is a fascinating place because everything else around it is metamorphosed.
It's an
strongly
orphan.
So just hammered. And then this is
Oh, wow.
Yeah. Okay. And there's very little outcrop. So.
Okay. Well, I think we got there. If you wouldn't mind stopping your share, man, what a ride that was. Holy cow. I loved that.
That. It's like I said, this was I was thinking, well, this will be an interesting conversation because it is completely different from everything you've been focused on. But it's in a lot of other people's reconstructions, they have it as all together and just mostly extension and collision rather than not much translation.
Yeah.
And so that's why I started out with the headline is it's convergence and translation are the key words. There's local extension, but that's not what is controlling the map pattern. And that's not what's controlling the dominant process. And yet, when you're right, when you look at maps and people's reconstructions, most of them don't try to deal with the vast amount of strike slip.
Right.
That to me, and I get it. It's hard. It hurts. Somebody said it makes my head hurt. And I'm like, yeah, I know. That's, but we're not here looking for the easy outs, right?
No, we're not. Well, Dr. Sarah Roeske, please hold the line. I'm going to stop the recording. Sure. We can chat for another minute or two. But I mean, that was, I don't know how much more we're going to get from you. That was a huge piece for me that I'm going to be thinking about the rest of the holiday break.
Okay.
Thank you
I
so
hope you
much.
don't think about it too much over break.
No, to hell with the family. I'm going to be thinking about this the whole time. So
okay.
Thank you for your time today, Sarah.
Yeah, you're welcome.